In the previous lecture, we have derived the first-order model of the CPM controller. We have validated its advantage of simpler dynamics. So in today's lecture, we are going to analyze its disadvantages, which is the instability issue. And we will also discuss about how to solve this issue. So first, let's discuss why this stability issue will occur in CPM control. So basically, there will be an oscillation happening when the duty cycle is bigger than 0.5. So before we talk about the oscillation issue, first let's look at the steady state operation of CPM. So we plot the inductor current waveforms and also the controlling current waveforms. So suppose that here is the controlling current, IC. And the blue line indicates the inductor current, IL. So here we denote as IL0. So when the switching cycle happens, the inductor current will rise linearly, right, with the slope of M1. So this marks the operation mode for 1 from 0 to DTS. So starting from 0 to DTS, so we can find out the expression for the ending current for mode 1, which is denoted as IL DTS. So based on this straight line, we know its initial value and its slope, so we can easily find out the ending current here, right? Ending current here, which is the beginning current IL0 plus the slope, which is M1 times the duration of mode 1, which is D times TS. So at this moment, it equals to ICT. When it hits ICT here, the switch will be turned off, so the current begins to drop, starting from DTS until the beginning of next switching cycle. So from TS, DTS to TS, we can write the expression for the ending current here. So equals to the beginning current, which is IL DTS here, minus the drop of the inductor current in mode 2. So which is the slope. We denote that the slope here is minus M2, right? So that this equals to minus M2 D prime TS. And this equals to, we insert the expression for IL dt to here, right? So it's IL0 plus M1 DTS minus M2 D prime TS. And also, based on the formula 1, we can derive the expression for duty cycle, right? So we move this IL to the right-hand side, divided both sides by M1 TS. We can solve the expression for D, so which is M1 TS ICT minus IL0, right? And at steady state, we consider that this is steady state. So at steady state, So we would have that the ending current over one switching cycle equals to the beginning current. That is basically the definition for steady state operation. So IL TS should be equal to IL 0. So let's look at this formula, right? If IL TS equals to IL 0, so it means that this part will be equal to 0, right? So we rearrange this formula, we will see that M1 dTs should be equal to M2 d prime Ts. And the Ts can be cancelled on both sides. So we consider steady state, we will replace the lowercase letters by the capital letters to show that this is the DC quantity. So we can find that capital M1 D equals to capital M2 D prime. So based on this, we can derive that M2 over M1 equals to the ratio between D and D prime. So later on, we are going to use this conclusion. We first put it here, okay? So next, let's look at what if the inductor current is perturbed. So what would happen? So I'd like to plot a separate plane to show you the changes. So here, time domain. Y-axis is the currents. Same, we have the controlling current as ICT. And we put the unperturbed inductor current as what we plotted here. So this is the IL 0. This is DTS, right? This is TS. Slope here is M1, M minus M2, M1. So now let's introduce a perturbation into the blue curve. Let's see we insert a small signal perturbation on top of IL. So let's say that I use the yellow chalk to show you. So here we introduce a change on top of this, right? So which is IL small signal T, small signal 0. So it's like the IL 0 is shift up by this amount of small signal change. Then in mode 1, the switch is on, so the current continues to rise linearly until it hit the ICT, right? ICT, then it enters into the next mode, so switch is off until it reaches the next switching cycle, TS. So if we look at here, this will be the transition point from mode 1 to mode 2. So the transition point is shift to the left by a small signal perturbation of duty cycle, D cap TS. And at the end of the switching cycle, you will see that the ending current is moved from here to here, but also by a small signal quantity we denote as IL cap TS. Okay, IL cap TS. So the blue line is ILT. So based on the waveforms I plotted, we can try to analyze the relationship. First, we look at IL cap 0, right? IL cap 0. So IL cap 0 is shifted to here. So this length equals to this length because it's parallel, right? Parallel relationship between the two sides, right? Two sides. So this equals to this quantity. Then we look at this small, very small right angle triangle, right? Right angle triangle. So this side equals to IL cap 0. And the slope of this side equals to M1. And the duration equals to d cap minus d cap Ts. So that we can, based on this relationship, right, this triangle relationship, we can derive that IL cap 0 equals to minus M1 times d cap Ts. And this is because d cap Ts is a negative number, right? It's pushed to the left-hand side, so it's negative. So we have a minus sign here. And the next, we look at this shape, right? It's also paralleled, so that the IL cap Ts should be equals to this side of this triangle, right? This triangle, right angle triangle, right? So here is like IL cap Ts, and the slope of this side is minus M2, and the base equals to d cap Ts. So similarly, we can also derive the relationship between IL Ts and d cap Ts times M2. So here is positive sign, right? Positive sign. So based on those two relationships, we can calculate, we can basically eliminate the common parts, right, such as d cap Ts. So we find that the IL Ts equals to IL cap 0 times the ratio, right? The ratio between M2 and M1. So based on the conclusion we made here, right, you'll see that M2 over M1 equals to d over d prime. So equals to IL 0 minus d over d prime. This means that over one switching period, the perturbation is amplified by this minus d over d prime times, right? So let's consider what happens if the perturbation lasts over n periods. Over n periods. So one period is minus d over d prime. So n periods means that minus d over d prime to n, right? So IL to n Ts will be equal to IL 0 times minus d over d prime to n times, right? So this will be the key indicator. So if the duty cycle is below 0.5, then this minus d over d prime will be smaller than 1, right? So the absolute value of d over d prime will be smaller than 1. So the number smaller than 1 to n, the power of n, right? Meaning that if n approach to infinity, this will approach to 0, so that the perturbation will be decayed to 0 if n approach infinity, right? So this will approach to 0. However, if duty cycle is higher than 0.5, so this absolute value of d over d prime will be bigger than 1. The number higher than 1 to the power of n, right? If n approach to infinity, this power will also approach to infinity. So the perturbation will be amplified and amplified until it goes to unstable, right? So that goes to infinity. So this means that the system will be unstable. Right? But for this one, it is stable. So that's where the stability issue of CPM occurs. So in this section, we have analyzed the stability of the CPM control. And we found that when the duty cycle is bigger than 0.5, the noises in the circuits will be amplified with the time going, so which will lead to the instability of the system. So in the following section, we are going to start the how can we introduce a slope compensation to resolve this issue.